So I'm going to talk about a little bit of hindcasting about what the carbon and greenhouse gas consequences of the diking at Herring River have been over the past century, and then a little bit of forecasting to try to work out what the future greenhouse gas emissions are going to be in Herring River if we restore it or if we don't restore it. And it's going to draw on, the presentation is going to draw on a lot of the data that Jim and Megan just showed us, as well as data from other people. Okay, thanks. All right. So within the Bringing Wetlands to Market project, we identified tidally restricted, impounded, and freshened wetlands as important coastal carbon feature, and estimated that those kinds of wetlands could be important and manageable methane sources. And this is just a small example in Woods Hole, Massachusetts. This used to be a railroad here. It's now a wonderful bike path. But when they built this railroad, they cut off the openings to all these wetlands and estuaries all along the coast. And so that we have a very wide distribution of tidally restricted wetlands because we have a lot of roads, a lot of railroads, a lot of dikes, a lot of infrastructure at the coast. Why do tidal restrictions drive greenhouse gas emissions? And the reason is because hydrological management has substantial consequences for all of the ecological processes in a wetland. And these diagrams here, I'll briefly recap some of what's already been said about what the effect of altering the tidal flows in wetlands are. So this up here in the top left is a natural wetland, or possibly a restored wetland, and it has a high rate of carbon dioxide uptake, a lower rate of carbon dioxide emission, so it's got a net gain of organic matter in the soil, as Megan just talked about. That builds soil volume, which builds elevation over time in response to sea level rise. They have low methane emissions because they're inundated with seawater. Seawater has high concentrations of the sulfate ion, and so microbial processes under anoxic conditions tend to be through sulfate reduction instead of methanogenesis. So they don't produce much methane. And so on the whole, they cool the climate. If we impound a salt marsh, we hold fresh water that should be draining off of the landscape on that wetland. And so it tends to freshen. We keep a high water table and a low salinity. It becomes a low salinity wetland, possibly a fresh wetland, or maybe an impoundment with standing water. And so we've blocked that sulfate ion that I just mentioned. And so we get more methane production in that case. We also lose soil volume. And so we convert what was a cooling system into a climate warming system. If we put a dike across in front of a wetland and we put flapper gates, tide gates that allow water to drain off the landscape, but it doesn't allow water to flow onto the landscape with a rising tide, then we drain that landscape. And so we convert what used to be a salt marsh into an upland. You might get vegetation growth on it, upland vegetation growth. You get that oxic breakdown of the soil organic matter, as Megan just described, and you can get a massive carbon dioxide emission, and you lose volume. So this graph down here on the bottom left is showing radiative forcing, so the impact on the global climate system of managing an example ecosystem. And here we have natural salt marsh on the negative side, and here we have the potential magnitude of tidally restricting wetlands. So it can be a very large impact per unit area. And then since the impact is large per unit area, that means that if we have a lot of these areas, then they're just generally significant on a continental or national scale. And we've estimated that in the United States, that there are in the range of about 500,000 hectares of tidally restricted and freshened wetlands. And this is a coarse estimate, and we're working on improvements in that estimate. That would produce about 12 teragrams of carbon dioxide equivalents per year of anthropogenic methane. And this is just an example. This is Buzzards Bay here in Massachusetts, and each of these symbols indicates a restriction on tidal flow between an estuary and the coast and the ocean. In terms of geographic distribution of diked and drained wetlands, Kroeger et al., a paper that Ariana mentioned earlier, have estimated that there are around 250,000 hectares of drained former tidal wetland in the United States. And this is the Herring River dike here, and these are not from the Herring River, but it's an example of flapper gates and a drainage ditch that would produce drainage. So what happens in more detail to the hydrology of a wetland when we build a dike across it? I have some diagrams here to indicate what the concepts are. So this is the natural tidal range outside the Herring River dike. This is the tide range inside the Herring River dike. So the range has dropped quite a lot, and on the whole, the average water level is lower. So in this diagram below here, we have the tide range in the ocean that is controlling the distribution of high salt marsh and low salt marsh and subtidal mudflat areas. So the tide rises up to this area in some cases, and it'll drop as low as the low salt marsh in some cases. And so this is a cross section of the landscape. As we move past the intertidal zone into the upland, you have a fresh groundwater lens that is poised hydrostatically against that sea level. So it's got rainfall and evapotranspiration on the watershed. There's drainage towards the coast, and the elevation of that aquifer is significantly determined by the elevation of the sea. And then as a next step in a sequence of conditions, the position of that fresh water table on this kind of a single watershed scale largely controls the distribution of vegetation. So if you have very high water table or a low elevation relative to the water table, you tend to have a wetland. If you have slightly higher water table, you'll tend to have shrubs and grasses, and where the water table is deeper, you'll have trees. So what happens when we dike it? We hold back the sea. Oops, wrong one. We hold back the sea here with the dike. The water level drops. The fresh water table drops along with it, and this former salt marsh here becomes upland, and it grows trees, shrubs, upland grasses. So what does that mean for the carbon and the greenhouse gases if we try to pull all that together in terms of what's happened already in the Herring River system? So this is the dike here. The Herring River has many arms that go up in these various directions. So people have mentioned it's about 1,000 acres or 400 hectares, and it has several different kinds of vegetation on it now. Each of those settings with different water table depths, different vegetation covers, has their own rate at which they photosynthesize, their own rate at which they store carbon in the soil, their own rate at which they grow woody biomass, their own rate at which they produce methane. So we needed data across all those systems, which has been shown already in the previous two talks. So if we try to pull together those processes across the whole system, we can try to estimate what's happened in the 100 years since Herring River was diked. So we can do that by looking at emissions measured in current day conditions and hindcasting back to a natural salt marsh system that was present a century ago before it was diked. We have to account for the fact that previously this woody vegetation that's grown up into the shrub and the forest areas wasn't there, and that represents a carbon stock that's built up over the 100 years as well. The future projections under full restoration are based on SLAM modeling, which was done by the Woods Hole Group for the National Park Service. And they essentially indicate that the system will be dominated by saline or brackish salt marsh in the future after restoration. But what we need to compare to this future condition after restoration is not what the system is like now versus what the system is going to be like in a century. Instead, we have to compare what the system will be like in a century if we restore it versus what the system will be like in a century if we don't restore it. So our efforts now are to try to figure out what that future condition is in a scenario without restoration. And our hypothesis is that the vegetation, the soil, and the greenhouse gas processes in Herring River, as well as in other diked wetlands, will be controlled by groundwater rise underneath the landscape, because we have a dike holding the sea back, and so sea inundation can't occur in these diked wetlands. Instead, what will happen is that groundwater that's hydrostatically poised against the sea level will rise up underneath that landscape and cause a transition in vegetation, carbon storage rates, and methane emission rates. So what might that look like? This is another graph similar to what Megan showed a few minutes ago. So this is water table depth below the land surface in the Herring River system now. This is 0.8 meters. So the water table is not very deep below the soil surface. And keep in mind, this was all once intertidal. So the sea level has risen about a foot or so since it was diked. So these are all very low landscapes. And what you can see is that where it's wooded, the water table is deeper. Where there's shrubs, it's less deep. Where there's cattail wetlands, it's yet shallower. And where it's shallowest, we have Phragmites invasion. And so what we're suggesting is that as sea level rises, it will drive this water table shallower and shallower over the next decades towards this kind of a system here. So we'll have a groundwater rise-driven succession from wooded to shrub to probably Phragmites ultimately. And I have another set of diagrams I'll show to try to show that conceptually a little bit further. So what we're doing is we're taking sea level rise projections for this area. There's some model estimates for sea level rise for the United States that's developed by NOAA and it's hosted by USGS that takes into account local land motions, takes into account changes in gravity fields around the Earth with deglaciation, with melting of ice sheets. And what they show is that in this particular area here in New England, this is very small here, it's hard to see, but if we have a 1 meter global mean sea level rise during this century, that will translate into about 1.3 meters of sea level rise here. And so we're taking a scenario right now with this 1 meter global mean sea level rise, and we're developing with collaborators a model to estimate what the groundwater response will be to that level of sea level rise. And so what we're seeing so far, and this is a preliminary analysis, is that rate of sea level rise would be projected to drive forest and shrub ecosystems to transition towards herbaceous wetland around mid-century. We would also expect, it's likely that when the water table becomes shallower and it's a low salinity water condition, that as the trees and the shrubs die, there's going to be a tendency for Phragmites to invade those newly opened habitats, those new ecosystems. Phragmites likes a water table that's a little bit below the soil surface. That'll give it a good opportunity when the vegetation dies to get established. But it can hang on even when the water table is substantially above the soil surface. So we're anticipating that Phragmites expansion is likely. So here's another cartoon to show what we're talking about. So here we have present day sea level, and here we have the dike, and we have this mix of vegetation across the landscape with the fresh water table poised against the sea level. And as sea level rises, the groundwater starts to rise towards, and in some cases above, the soil surface. Where it gets very shallow, we'll tend to have expansion of wetland vegetation such as Phragmites, and trees and shrubs will start to die. There's already a lot of evidence in the Herring River system of quite a lot of dead tree and dead shrub coverage in the watershed. And with yet higher stands, the entire system will likely be near inundated or possibly inundated And that's even considering that we expect the soil surface to continue to rise, as Megan was showing. Phragmites, all these kinds of ecosystems, they do build soil carbon stocks. They'll rise, but the water level will rise faster. So it's headed towards a freshwater impounded condition instead of the largely drained condition that it's at right now. And as Jim showed you, the freshwater impounded condition does lead to more methane emission, particularly where we have Phragmites invasion. It seems to have extremely high methane emissions. So our preliminary estimate of greenhouse gas emissions to the atmosphere in the 100 years since it was diked, we arrive at a number. Where do I have the number written here? I guess I don't. Well, we have here 4 bars. So on the left, we have the amount of soil carbon loss. That's that loss of elevation that Megan was showing. And here we have the growth on the negative side. We have a removal of carbon dioxide from the atmosphere due to growth of woody plants. And thank you, by the way, to Jackie Foose, who worked with Tim Smith at the Park Service for doing an incredible amount of work to figure out how much woody biomass exists on that ecosystem. In the 100 years since diked, this is the climate impact and CO2 equivalents of the methane emissions that have occurred. So here we have total net emissions since diking, which is equivalent to driving 155,000 modern US automobiles for a year. So it's a significant impact due to diking this wetland. So what that says first is that preventing degradation of our wetlands can be a significant benefit to climate in the first place. So how much greenhouse gas emission do we expect until the year 2100 if this system remains diked and is exposed to sea level rise as projected? And what is the net greenhouse gas emission expected if it is restored? So has the same graph that I just showed you, and it's sitting next to 2 other graphs. One is net greenhouse gas emissions till the year 2100 if it remains diked, and here's the restored condition. So if it's restored, we expect quite a lot of new carbon sequestration on the negative side. We have a small carbon emission from killing all of that woody biomass that exists there now. That's going to respire and go back up into the atmosphere as carbon dioxide. We'll have a modest amount of methane emission under that restored condition because it'll be higher salinity, and therefore the methane emissions will be reduced. And so on the whole, we have a negative greenhouse gas budget for the system over the next century if it is restored. So if we were to compare the current condition to this, we would estimate a moderate amount of benefit to climate from the restoration. But if we compare that future condition with restoration to a future condition without restoration, taking into account groundwater rise underneath the system, this is our current estimate for what the greenhouse gas emissions would be under those conditions. It would continue to store more carbon in the soil, not quite as much as an intact salt marsh, but we would project quite a lot of methane emissions over the next century in the impounded and freshened condition that it would be in for a portion of that century. So the difference that we need to look at is this blue bar here versus this blue bar here. So a large greenhouse gas emission to the atmosphere versus a moderate greenhouse gas sink from the atmosphere. So the difference between those two is about 1.8 million metric tons of carbon dioxide equivalents, which is equivalent to driving about 380,000 cars for 1 year. So it's a pretty substantial benefit. The town of Wellfleet, where most of this system is, only has about 4,000 people in it, so they can't possibly drive that many cars. So it's significant compared to other options. So take-home messages. Dike and drain landscapes progressively lose elevation and on some time scale are unsustainable because of that groundwater rise underneath them. The time scales of change may be predictable based on modeled groundwater rise and soil accretion or loss. There's a risk that poor wetland management can cause soil carbon to be reduced to the atmosphere or emitted to the atmosphere as carbon dioxide or methane. Degraded or altered wetlands are an opportunity to reduce an anthropogenic greenhouse gas emission while enhancing elevation resilience. So our biggest two opportunities may be for greenhouse gas management in tidal wetlands may be avoiding degradation and destruction in the first place and restoring these tidally restricted wetlands. And finally, restoration of the Herring River system is expected to produce substantial climate benefit. Thank you.
Thank you, Kevin.
Sure.
One question for Kevin. One? Yes, Ariana.
So have you presented this particular story to any policymakers? Because it feels to me like this is particularly useful to say, okay, right now, some benefits, but if we don't do anything, like we got to do it now or it gets even worse. That seems incredibly compelling. Have you tried that yet?
I think I am right now, maybe,
Okay.
possibly. I mean, that's, yeah, it's a good question. I think some of this is new. It's, because, in the past, it's not that people haven't known that we should look at the future scenario for the best comparison to future restored condition, but there just wasn't the information to do it. So we're trying to develop that information, and it does indicate that the benefit will be shown to be significantly greater if we do that proper comparison. I've had, a variety of conversations, some presentations with people at the National Park Service and various other agencies, spoken to people at NOAA. They're noticing the information, but this particular piece is still in development as a publication, and it'll be easier to promote once we get it published.